Is well caffeinated after the coffee break. So, I want to start with a story. A couple of years ago, I was working at a small startup. Our code base was written in Scala, and there was enough issues with it that we decided to completely overhaul our architecture. But we wanted to do it right. We were going to be functional. We added Scala Z. We added the state monad. It was going to be beautiful until we started seeing Stack Overflow errors. And this was just in testing. We hadn't even deployed this to production yet. So my coworker says, let's just trampoline it and add the free monad. And this is me having no idea what he meant by that statement. That was the first time I'd ever heard of the free monad, and I didn't know what my coworker meant or why he intended it to solve our problems. And then a couple of years later, I'm at a different startup in a different Scala code base, and there was one application there that no one wanted to touch. And I looked at the code and I understood why. It was a data application with a really simple purpose, but the code made it look really confusing. And that made small changes take a long time. This might sound familiar to some of you. So I wanted to know if I was justified in being annoyed with this application that was using free monads to abstract this data store. So I decided to figure out what the heck a free monad is so you don't have to. My name is Kelley Robinson. I am a data and infrastructure engineer at a company called ShareThrough in San Francisco. And today I'm going to talk to you about why the free monad isn't free. A couple of things about myself. I am an industry programmer. I have no background in academia. And I think this talk is really interesting for a venue like this because I know that my opinions about the free monad have people that agree with me and people that disagree with me. And there's definitely a mass on each side of the argument. So it's good to have the conversation and get this out there to see what people think. So before I talk to you about why the free monad isn't free, I promise to explain what it is, and we are going to do that using monoids and functors to build up our explanation, to understand what a monad is. And then we'll talk about the free versions of these structures, why people use them, and maybe why you shouldn't. And then if you don't use the free monad in your code, what are the alternatives available to you? And then wrap up with talking about some of the real world applications of this that we do see. This presentation has a lot of code. It's all in Scala. If you're not familiar with Scala or want to look at this later, everything's available on my GitHub. Here's the link. Okay, we've probably heard monads are monoids in the category of endofunctor. What does that mean? We'll start with monoids. We're not going to explain this using category theory. This is, the ideas for these structures come from mathematics, but in a language like Scala, you don't need the mathematical definitions to explain them. There is a way to explain them using the language. And so these are ideas in a language like Scala. We have to implement the structures. And so for a monoid, this is some type that follows some properties. It's going to have a method to append to take two of that type and turn it into a single instance of that type. And then some method, usually called identity, that's going to be a no-op, or empty. So again, two of one type coming together to produce another instance of the type. That is a monoid. And like I mentioned, there are some properties that it follows. So identity is a no-op when it's going to be used with the append method. And then there's this idea of associativity, or saying that the grouping, you can think of it with parentheses or in any other way, that's not going to matter for a monoid. And Buzz Lightyear is right. There are monoids everywhere. We can look at a couple examples. String concatenation, really great example of a monoid. For this example, the append method is going to take two strings, put them together, and return another instance of a string. And then the identity method, the empty value here, is going to be the empty string. Another example, integer addition. This is another great example of a monoid. You can take two integers, put them together, and you have another instance of an integer. And the identity value in this case is going to be 0. Okay, quick overview of monoids. Let's move on to functors. A functor is going to be a family of types that is going to apply it has a map method, and the map method will apply some function to everything in that family. And then it will return a new container. If you want to look at this with pictures, you can think of it as applying function there. The function in this case is multiplying all the values by 2, and then returning the new container with all of the values in the container multiplied by 2. The result is on the right. Like with monoids, functors have some properties that they follow. You have the identity value, which is going to be the no-op function that if used with map is going to not change the input. And then composition is like associativity that we saw with monoids, but that's to say that the grouping doesn't matter. And that's if you chain a bunch of map operations together. It's the same thing as doing one giant map with a bunch of logic in it. And that brings us to monads. I really like this quote from a Stack Overflow post that says the term monad is a bit vacuous if you're not a mathematician. An alternative term is computation builder. So this audience might have some mathematicians, but for the industry folk among us, this is a really helpful mental model. So a monad is some type that's implemented the pure and the flat map methods. It's a container, a context, a collection. The pure method is going to lift a value into that context and create the computation builder. And then the flat map is kind of like map. It's going to, like a functor, map over the values in the container, apply a function to it, and then flatten the context. And we'll see what that means. The interesting thing about defining monads like this is because now we can work backwards to define the functor and monoid operations. Once you've defined pure and flat map, you can define map. More explicitly, you can see here how map is using the flat map and pure functions in its implementation. And so the Scala code here has abstract definitions for pure and flat map, but then it's implemented the map function without needing to go back and do that separately. And flat map can also define the monoid operation of append. And I've been very explicit about how I've defined this here, because the append method here is evaluating the functions as it's chaining operations together, composing them, and then returning the new value. So monads also have some properties. The laws apply here. Flat map with some identity value is going to be a no-op. And then composition follows. The grouping of the operations won't matter. You can do a giant flat map with a bunch of logic in the function or chain a bunch of flat maps together. So if we look back at our picture example, for functors, this is what it looked like when we were mapping with a function. But what happens if that function that we're mapping with also creates a new context like we saw here? If you map this, then you're going to be left with some nested triangles. The reason that flat mapping and monads are useful is because it does flatten those contexts. When you flat map over this kind of operation, you're left with a flattened context in a single triangle. And that's why monads are useful. They're useful for composing functions for values in a context. Mapping allows composition. And this type of construct is really useful for managing side effects. Monads make side effects explicit, and we see this everywhere in our programs. You can think of things like lists and futures. And if you go back to the triangle example, we don't want to be left with nested triangles, just like in the returns of your programs, you don't want to be left with nested futures. Okay, now we've defined what those structures mean, we can talk about the free versions. Before we do that, though, what do we mean when we say free? When we say free, we mean free to be interpreted in any way. Free in the sense of unrestricted and not zero cost. Or, for the Richard Stallman fans in the room, free as in freedom, not free as in beer. So there it is already, the free monad isn't free. But in order to build up our understanding, we're going to again start by looking at the free version of monoids. So we'll refresh our definition of monoids. We have an append method and some identity method. And in order for a monoid to be free, we want it to be free from interpretation. And that means there can't be also any lost data during that append step. And that's pretty vague, so we'll look at an example. List concatenation is a good example of a free monoid. In the append step here, we're just shoving the data together. We're not losing anything about the data that we shoved together. And it's also important here that we define this with the generic type A. The contained type in the list could be anything. It could be ints, it could be strings, it could be other complex types. But because it's generic, the only operations that we can do on it are the monoid definitions here, the methods that we've defined. And that keeps it free because we don't know anything else about it, and therefore we can't interpret the data in any special way. Keeps it free from interpretation. In contrast, if we look at our integer addition example, this is not free because we're losing information about the input data when we transform it into the added integer. There's a special algebra that's happening here that is not free from interpretation. It's an explicit interpretation for the type. And that brings us to free monads. In order for a monad to be free, we don't want to lose any data, and that means no evaluating functions while we're chaining operations together and while we're flat mapping. If you look back at our example that we used defining these pictures, these triangles, this fails the free test. We're evaluating that function and losing data in the result. We don't know what the function was, and we don't know what the input data was in that final result. So how do we do this without losing the data? The important thing is that we have to store the data and the functions as we chain operations together and effectively build up a syntax that we can evaluate at a later point. So I'm going to walk through how we would do this in Scala. We'll start with a trait, we'll call it free. We'll add a class return that's going to be used in our pure function and to indicate that there's no more computation. And then we'll add a class suspend that's going to take some family of types A, and it's going to be used to suspend the computation of that container until we're ready to process it. And then we'll add a class flatMap that's going to take another instance of free and a function from any type A to another instance of free. And this looks a lot like the method signature for flatMap, and that's going to help us out. And finally, we'll add some helper methods on our trait that will be used in the computation and allow us to chain our operations using the Scala syntax. And we're going to use this to build up the types, to store the syntax and the functions. But again, we're not going to evaluate anything when we do this. We just want to store it. So let's look at an example. Let's build a free monad for actions on a to-do list. So here we've defined some syntax for things that you can do to a to-do list. You can create a new task, you can complete a task. And then we'll also add some methods that are going to lift those operations into our suspend case because we want to suspend the action until we're ready to interpret what we want to do. Again, these functions aren't doing anything, they're just talking about what we want to do. And this is why it's free. It's free because we haven't done anything. So let's see what this looks like. So in Scala, this is pretty cool. You can then chain these together using a for comprehension, and that's syntactic sugar for flat mapping. You could write this as another way using flat mapping in most languages. And this is great because it is chained, and this might look familiar to programs that you write, especially in Scala. The difference here is that nothing has actually happened yet. So we can expand this into its resulting data structure, and here it is in its explicit types. And you can see this is a big nested data structure where we're storing all of the information about what we want to do. We're shoving the data together as we chain it. Nothing has been evaluated, there aren't any operations defined, and that's why it's free. Again, if we look back at our previous example, this isn't free because the result has lost the input data. The corollary to this in the free monad world would look something like this. You would store the input data with the methods. And this is free because in our minds, we know what the star function means, but we could interpret that to be anything in a later point. Okay, why would anyone do this? Why do people want to use free monads? There's a few reasons. A lot of people talk about deferring side effects. I mentioned that monads are really useful for managing side effects, but free monads make it possible for you to truly defer them. You're composing functions without computing them. And if you delay all of that evaluation until a later point, that means you're delaying all of the execution and the side effects until that later point. And the syntax tree that we defined, that DSL, the domain-specific language for our to-do list, that means that we can define multiple interpreters at that later point, at the evaluation point. And that can be helpful in a couple of ways. It's like if I write down a list of instructions and hand it to everybody in this room, you're probably going to interpret that a little differently. And we can program those interpretations of the list or the structure that we give you. And then if you imagine something like this, some nested function that's doing a lot of looping, these do something functions could do a lot of things in the course of your programs. But that's just it. In the course of your programs, it's going to look something like this. Every function in the monadic context is going to be added to the stack. So remember my coworker? Let's just trampoline it and add the free monad. When we talk about trampolining, we're talking about expressing all of the control flow, all of the function passing, all of those chained functions, putting them in a loop instead of putting additional functions on the stack. The free monad uses trampolining when it's doing its evaluation, and it exchanges stack for heap. Trampolining and the free monad all come down to exchanging stack for heap. We built up these data structures. That's the putting the data on the heap instead of putting additional function calls on the stack. In the not free version of this world, your result would look something like this. You would have a bunch of functions that would be stacked up, that would be putting all these additional function calls on the stack. And in the free version of this, your result size, your data structure, the heap that you're using would grow and grow with all of the information until you're ready to process it. So if we look at the example that we built up, this chain data structure, we built up this list-like syntax, and we have already avoided putting function calls on the stack, and so we want to make sure that we don't let that work go to waste, and so we want to evaluate it using a loop. And so let's talk about what it means to evaluate a free monad. We'll look at the function signature for what this looks like in Scala, and we've written a generic function here for how we would do this. And this is going to take some input, your free monad. It's going to take some transformer that's going to take your free monad input and do the translation, do the evaluation into your output type. And then we also have this implicit condition that the transformed type is also a monad. And that means that we can stop the execution in the chain so that we can use something like flat mapping with the context. The functor transformer is a tricky part here, but it's what allows us to have one generic run function and define those multiple interpreters that I talked about. So again, just wanted to touch on this real quick. You might also hear functor transformers called natural transformations. I think that name doesn't make any sense, and so I wanted to be more explicit about what it does, because it's taking one functor and turning it into another. Okay, this is the function body for the run function. And this is already a lot, so I've intentionally left a lot of it off. But here it is in total, and you can look at some of the important bits. And the points I want to point out are that this is going to use tail recursion, and that's going to do the looping. In a language like Scala, tail recursion optimizes recursive calls and puts them into a loop instead of putting additional functions on the stack. And so that's using the trampolining. And then it's going to pattern match on the return, suspend, and flat map cases in order to evaluate the functions. If we look at what happens in those cases, I wanted to point out what happens when it hits the suspend case, and this is where the transformation happens. This is the interpretation. This is the evaluation. And so we'll look at what some of those interpreters look like, but first, I wanted to point out that we can be even more explicit about how we do this. We can write this using a loop. And if you're someone that's used to functional programming, looping seems scary and really non-idiomatic to some languages, including Scala, but I just wanted to point out that this is doing the same thing. The logic here is the same as it was on the last slide, but we can be explicit about it. We can be explicit about the fact that we're looping and using the trampolining to achieve our goals. So a couple notes about evaluating. We want to apply the transformation on the suspend case, and we want a trampoline for stack safety. That's, again, using the loops. So let's revisit our functor transformers, the things that are going to be doing the interpretation. And we can look at a couple of interpreters that we can define for our to-do list example. So we can define a test interpreter. And I've defined a trivial context here, that id type. And that's going to, our test interpreter here is going to take a mutable map in place of whatever production service you're using, probably a database. And then we can look at the apply method here, what's going to create this interpreter when you instantiate it. And so this is where it gets interesting. This is where that domain-specific language comes in handy. We're going to evaluate our to-do list syntax and perform an action based on what the syntax is. And this is where all of that interpretation is coming into play. This is where you actually define what your program is going to do. And in this test interpreter, we're going to build up the model based on what the action tells us to do. And this is how you would run it. You take your to-do list function, the to-dos there, feed it to the run free function, and then give it an instance of the interpreter that you want to use. And then we can compare it to our expected map. For something like this, though, this test might be shadowing some business logic. We put some Boolean logic in there, and that might defeat the purpose of testing. So we can define a different type of test interpreter. And so the action test interpreter here is going to start with a list of actions, and this is also going to test the order of actions that we expect. And so here, when we pattern match on the syntax, we're going to append the action to the actions list, and then when we run it, we instead expect a list of actions in the order that they occurred. And the cool thing about this is that your production interpreters are probably going to have side effects. You're probably going to be writing to a database, and that could cause problems for you. So defining multiple interpreters and defining test interpreters like this allows you to test that side-affecting code without using things like mocks. And this is a really common use case for things like the free monads. People love doing this. They think it's much more clean than using something like a testing mock. So we can look at an example of the production interpreter here. I've written it here to transform to a Scala option type that's either some or none. And this doesn't have to be the same return type as it is in the test, and it's probably not going to be. But it is important that that transform type is a monad so that the chained operations will stop if this fails, in this case, if this evaluates to a none. So again, some of the justifications, some of the reasons that people talk about wanting to use the free monads, we really want to defer those side effects. And I don't know of another better way to truly defer side effects than using something like this. And then you can talk about the multiple interpreters. In production, you're probably going to be writing to a database or doing an HTTP request or queuing messages to some service. And then in test, you can suppress all of those actions and instead return the expected actions that you want to see. But the thing about things like the free monad is, as industry software engineers, a lot of people introduce these concepts into their code base simply because they can. It's a neat solution, but I always get nervous when I see neat solutions in industry code because it usually means that there's an easier way. There's this really excellent talk from Jessica Kerr at a Scala conference last year where she talks about scaling intelligence, this idea of blue sky Scala, the meat of our business logic that's somewhere between the green grass, the easy stuff, and outer space, the complicated stuff. The free monad isn't free because it's in that outer space category. It's impressive, but the path to get there is broken. And why is it broken? Well, there's points like this, and this is pretty controversial, but this comes from Marius Eriksson, who's one of the architects at Twitter. And this was in response to a discussion about calling a method in a library a mathematical name when the method didn't exactly map to the mathematical definition. And so his response to this is that programming isn't math, and sometimes we hoist vocabulary that confers similar meanings. Some people think that programmers need to be mathematicians or that we can only make those literal translations, but I agree with Marius here. Part of the reason software has been so successful as an industry is because we're really good at adapting and automating ideas. And our biggest skill is exactly this: creating abstractions to translate ideas to machines that can perform them more efficiently than we can as humans. Think about it. Programming languages exist for humans. Otherwise, we'd all be writing binary, and who wants to do that? But we want good abstractions, things that make things easier for us as humans. You can think about it, what David Nolan was saying this morning about the ecosystem. We want to reduce the friction for the programmers. We want things that are going to make it easier for me to look at code that I wrote 3 months ago, or even 3 days ago, and understand what I was trying to do. The reason that this can be problematic is when the abstractions are more confusing than they're worth. I said that this is what we're good at as an industry, but it's also something we're kind of bad at. It's really hard to know when you found a good abstraction. The free monad is a mathematical concept that has been applied to the programming domain. It has good abstractions that I'll talk about, but for a lot of us, it's not necessary. And why isn't it necessary? Why should we avoid it? Well, there's stuff like the boilerplate, that abstract syntax tree, that domain-specific language that we defined for 3 actions on a to-do list. That's going to be a lot of code. And if something like a production system of yours, you're taking all of your implicit actions and turning them into explicit data structures. And libraries are starting to develop ways around this. They're starting to develop some code generation, I've been told, but then there's still things like the learning curve. And it's easy to be frustrated with things like this, and it can take a really long time to grasp, and that's not only because they're difficult, they're not easy, but a lot of the explanations out there assume the wrong context for the learner. They assume that you're a Haskell programmer, or that you have a PhD in category theory, neither of which I had, and neither do a lot of industry programmers. And that can make things like maintaining this in production systems really hard. This can make it really hard for a team to maintain a code base containing these types of abstractions. We want to stay in the blue sky. We can take an airplane to get from point A to point B. A rocket ship is too expensive. So if we're not going to use the free monad, what are the options for us? Well, before we talk about the alternatives, it's important to know your domain. And I'm not saying that we can't use the free monad. I'm saying that we need to be mindful of the applications that we make. Like everything in programming, it's all about trade-offs and totally dependent on your domain. So first, know your domain. Especially for a language like Scala, there's a spectrum of how functional you can be, and a lot of people think of it in terms from Java to Haskell. Know the expertise of your team. This spectrum is relevant for Scala programmers, but think about the languages that your team is using. Think about the expertise of your team. A lot of my team came from Java, so we're pretty centered on this spectrum. I think we have a really good balance. We make use of the functional style, but we're not too far to the right there. And we're more likely to hire ex-Ruby or ex-Java programmers than we are ex-academics or ex-Haskell programmers. And so that makes it easier for us to stay somewhat centered on that spectrum. But in your domain, think about what your language is good at. Is it opinionated? If it's not, you have to make more decisions about this type of thing. And think about the abstractions you're using. Are they clean? Are they easy to understand for people new to the code base? And if you're writing a greenfield project, a new project from scratch, ask yourself, are your coworkers going to understand this? Do you have the time and the tooling for these abstractions? And is it necessary for your business logic? I think that's a big one that a lot of people don't ask themselves. So now we've talked about understanding your domain. What are the alternatives available for maintaining stack safety? Well, if your programs are more object-driven or imperative, I can definitely suggest using loops. And this is hard if you're highly invested in functional paradigms or if your language doesn't allow it. But keep in mind that looping can be better. In a language like Scala, you think about idiomatic Scala being using maps and that kind of thing, but if you look under the hood of the standard library, it's using all sorts of vars and can build froms. And these are ugly abstractions that are more efficient than using a traditionally functional style to do this. It turns out that looping and mutating state, which are things we shudder at as functional programmers, are more efficient. And so the standard library is this optimization on the common functional style. It's ugly, but it provides a good abstraction to us, and we don't have to think about it. It's a joke for any Scala programmers in the room. So, there's also alternatives for managing side effects. Again, I don't know of good ways to truly defer side effects, but you can definitely manage side effects with other options. You can use other built-in monads. You can error handle over exception-prone code. And keep in mind, not all side effects are bad. Things like logging are really helpful. I remember Heather Miller saying that at a Strange Loop talk a few years ago. Well, let's look at an example. So this is some code that a guy named Rob Norris wrote an entire library using the free monad called Doobie to abstract away the JDBC using the free monad. And he was saying there's too many problems with code like this. It's not safe. This can throw exceptions, and you can't chain the operations on the result set. And that's all true, but the only way to manage those exceptions isn't using the free monad. Error handling is good, but the functional programming overlords probably aren't going to smite you if you decide to throw this into a try except block. So here's a code example of something I wrote a few months ago. Sure, you can't chain it, but it works and it did the job that we needed it to do. It error handled over a database query so that we can make sure that that code was more safe. If there's an easy way to make something more functional, I'm usually going to take it, but it's all about the trade-offs and you have to keep in mind your domain. Okay, we can wrap up by talking about some of the applications that we see of this stuff. If this is something that you're interested in, you don't have to implement this from scratch. A lot of languages have libraries that have already been created for you, and some languages like Haskell have this built in. And then we can talk about some examples of things that I think have pretty good abstractions around the free monad. For all of my talk about alternatives, Doobie is pretty nice. It has some clean abstractions, and to the user, it is relatively friendly. And then we can look at something called Task from a Scala functional programming library called Scala Z. And this is a common abstraction for concurrent programming, and it's a good abstraction for multi-threading. And here's our example of enqueuing messages to Amazon's simple queue service. And it's a clean abstraction, and I'm really grateful for it because under the hood it looks something like this. And some of you might love working with type lambdas or understand at first glance what this does, but I don't want to have to. And this is the kind of code that motivated this talk from a place of pessimism because there was stuff like this lurking in production services. So what happened with my experiences? So at the first company, shortly after that coworker recommended that we introduce the free monad to solve our Stack Overflow errors, he left the company and we never added a free monad. And that was really good in that domain because at the time we were writing an API for a web app. And if we were seeing Stack Overflow errors, that meant we had grossly overcomplicated our business logic. I understand if maybe in your domains you have deeply nested logic and you can't avoid it, but in that circumstance we could. And then there was the data store app that was using the free monad as an abstraction layer. And I've concluded in the months and years since that I first encountered that the problems with that code base are largely unrelated to the fact that it uses the free monad. It was grossly over-engineered, and that is a problem when you start to introduce abstractions like this. And this is something that we have to keep in mind. As industry software engineers, most of us are getting paid by a company that is using us to make them money, and a lot of us don't have these large-scale problems that necessitate these kinds of abstractions. So again, know your domain. So after talking to a lot of people about the free monad, I'm still not convinced that it's the best solution. But I can see how if used wisely, it can create composable and safe code. It really comes down to the fact that we have to be judicious in our use of these abstractions. Just because we can doesn't mean we should. Sometimes it's okay to trade the most functional style for the sanity of your code and the sanity of your team. I like to say that you should assume competence, but don't assume knowledge. We have to share that. And if you're somebody that understands these and has the knowledge about these concepts, share it and make sure that you explain it in simple terms for people. Not everybody knows what a monad is, and you can't assume that they do. So I used to think that the free monad was a piece of crap. I don't think that anymore, but if you're like me from a year ago and somebody is talking about introducing this into your code base, I hope I've given you some tools to evaluate whether or not that's a good idea. Once again, my name's Kelley Robinson. Here's my contact info, and thank you for listening. Yeah.
So I was wondering, listening to your talk, do you think the problem is more that we have general purpose languages and maybe they are too general, and that the problem that we're encountering is more with the language than with anything else?
Yeah, so the question was, is this a problem because of the language and the language design is too general purpose? And I think that can be true for certain languages, especially in the Scala ecosystem. There's a lot of conflict around these types of subjects, and functional programming is not a first class citizen in the Scala language. And like I said, these are abstractions that you have to implement in the code if you want to use them. There's no built in monad type in Scala. And it's something that you think of lists and futures and options in Scala as monads, and they are, in theory, but they don't extend some monad trait in the back end. So a lot of people writing Scala don't ever have to know what a monad is. There's a lot of ways to write production Scala code that don't involve using monads. If you're writing something like Haskell, those are built into the language, and so I think a lot of the explanations are more relevant there, and they might do a better job of explaining it. But that's only if you're a Haskell programmer. It's not something that everybody that's a functional programmer does know or needs to know. Anyone else? Yeah.
Maybe it's also the fact that like you said, in some languages, monads are not really built in, but there are some other constructs which inherently are monadic. And maybe just because we try too hard in some languages to express monads in the theoretical representation, instead of trying to do something which would be monadic, it would solve a problem. Because what you're describing here, I don't know, I mostly do JavaScript. I can very much imagine it as some kind of lazy pipeline in JavaScript, which would only based on function could accomplish something very, very similar. And but it wouldn't involve at all doing something very theoretical. Like,
Sure.
sure, maybe just some people are trying too hard to push a theoretical representation of something useful.
Yeah. So the comment was it's a theoretical representation that is applied in the practical domain. And so in some languages like JavaScript, you have things that are using monadic structure more or less, but you don't have to use those words to describe them. Anyone else? Thank you. There was one application there that no one wanted to touch. And I looked at the code and I understood why. It was a data application with a really simple purpose, but the code made it look really confusing. And that made small changes take a long time. This might sound familiar to some of you. So I wanted to know if I was justified in being annoyed with this application that was using free monads to abstract this data store. So I decided to figure out what the heck a free monad is so you don't have to. My name is Kelley Robinson. I am a data and infrastructure engineer at a company called ShareThrough in San Francisco. And today I'm going to talk to you about why the free monad isn't free. A couple of things about myself. I am an industry programmer. I have no background in academia. And I think this talk is really interesting for a venue like this because I know that my opinions about the free monad have people that agree with me and people that disagree with me. And there's definitely a pen method is going to take two strings, put them together, and return another instance of a string. And then the identity method, the empty value here, is going to be the empty string. Another example, integer addition. This is another great example of a monoid. You can take two integers, put them together, and you have another instance of an integer. And the identity value in this case is going to be 0. Okay, quick overview of monoids. Let's move on to functors. A functor is going to be a family of types that is going to apply some, it has a map method, and the map method will apply some function to everything in that family. And then it will return a new container. If you want to look at this with pictures, you can think of it as applying a function there. The function in this case is multiplying all the values by 2, and then returning the new container with all of the values in the container multiplied by 2. The result is on the right. A mass on each side of the argument. So it's good to have the conversation and get this out there to see what people think. So before I talk to you about why the free monad isn't free, I promised to explain what it is, and we are going to do that using monoids and functors to build up our explanation, to understand what a monad is. And then we'll talk about the free versions of these structures, why people use them, and maybe why you shouldn't. And then if you don't use the free monad in your code, what are the alternatives available to you? And then wrap up with talking about some of the real world applications of this that we do see. This presentation has a lot of code. It's all in Scala. If you're not familiar with Scala or want to look at this later, everything's available on my GitHub. Here's the link. Okay, we've probably heard monads are monoids in the category of endofunctor. What does that mean? We'll start with monoids. We're not going to explain this using category theory. This is, is well caffeinated after the coffee break. So I want to start with a story. A couple of years ago, I was working at a small startup. Our code base was written in Scala, and there was enough issues with it that we decided to completely overhaul our architecture. But we wanted to do it right. We were going to be functional. We added Scala Z. We added the state monad. It was going to be beautiful. Until we started seeing Stack Overflow errors. And this was just in testing. We hadn't even deployed this to production yet. So my coworker says, let's just trampoline it and add the free monad. And this is me having no idea what he meant by that statement. That was the first time I'd ever heard of the free monad, and I didn't know what my coworker meant or why he intended it to solve our problems. And then a couple of years later, I'm at a different startup in a different Scala code base. And the ideas for these structures come from mathematics, but in a language like Scala, you don't need the mathematical definitions to explain them. There is a way to explain them using the language. And so these are ideas in a language like Scala. We have to implement the structures. And so for a monoid, this is some type that follows some properties. It's going to have a method to append to take two of that type and turn it into a single instance of that type. And then some method, usually called identity, that's going to be a no-op, or empty. So again, two of one type coming together to produce another instance of the type. That is a monoid. And like I mentioned, there are some properties that it follows. So identity is a no-op when it's going to be used with the append method. And then there's this idea of associativity, or saying that the grouping, you can think of it with parentheses or in any other way, that's not going to matter for a monoid. And Buzz Lightyear is right. There are monoids everywhere. We can look at a couple examples. String concatenation, really great example of a monoid. For this example, the